we learn all year that we will continue to use all year. And that is the concept of standard deviation. Now, when I was a kid, I think they did a terrible job of explaining standard deviation. So let me explain it to you in a good way. You know you've gone to Saturday markets where they sell artsy-fartsy sorts of things, yes? And you walk up and there's this gal, she's selling that kombucha crap.
Kombucha's awesome.
It's not bad. I used to make fun of it, but Mr. Fugier got me to where I don't hate it anymore. But it's just nasty. It's basically... It's basically if you like put your potato peels and your coffee grounds and crap, all the nastiness that comes off the bottom of that basically, and then you ferment it. Okay? Now, hey, so it's straight up, it tastes pretty good, it just sounds nasty when you talk about it, okay? It tastes pretty good. Now, you go to this Saturday marketplace, and this bottle's kind of brownish looking, because, you know, they just got it from some used place. This bottle here is shorter and whatever, and it's kind of this, you know, whatever color, I don't know. And this one here is really tall, and there's nothing at all standard about this kombucha stuff. Can you focus up here and shut up? Thanks. Now, when you go to Saturday market type places and it's artsy-fartsy, the fact that one bottle isn't as full as the next one, does that bother you? No, because it's part of the vibe. All right, that's what you're paying for. You're walking around. Oh, I got some art. We call it craft. You see, it's a craft beer or a craft kombucha. Okay, and the idea is, oh, it's so nice and everything. Listen, I guarantee you, you go to the store, and if you walk up to the milks aisle, and there's milk jugs sitting there, and the plastic. I can't draw plastic milk jugs to save my life. Okay, but there it is, and this one is down to here. This one, these are all the same, exact same size milk jugs, in case you're wondering. This one is filled up to here. This same exact size milk jug that looks exactly like the other ones is filled up to here. Which one do you buy? Well, first of all, I'll tell you this. You do not come over and buy this one. Right? Because why? Mr. Grum, it's terrible. But the person at the company said, listen, our milk jugs average a gallon of milk in each of them. I'm sorry, that's nice. They average a gallon. What if I get the one that I get screwed on? Okay. People do not buy your product at the supermarket if you put out crap like this. Now, kombucha at the Saturday market, sure, fine, it's great. It's craft after all. Okay. But no, at the store, when we mass produce stuff, we want quality control. We do not want to have this variation all over the place. I want to pick up this ketchup bottle and know without there beyond the shadow of a doubt, it's within 0.002 ounces of being 16 ounces of ketchup. I don't want to get screwed. I don't want to pick the one that's just not quite there. When you go to McDonald's, let's say you're out on a trip somewhere, just go with me. I'm going to talk to Matt Anderson back here. The rest of you just shut up about this, okay? Because I know you hate McDonald's. I'm a vegetarian. I'm a vegan. I'm a whatever. I don't care. Nobody cares. So I'm going here. Matt Anderson, you're on a trip somewhere. You're going to eat dinner. You have a choice between some fast food place that you've never eaten before it's a little weird. It looks a little sketchy. You got a little taco truck over here. It looks a little sketchy. You got McDonald's. You go to McDonald's. Why do you go to McDonald's? Because that's what you know. And when you walk in and you order a Big Mac, what does it taste like? It tastes like a freaking Big Mac. That's what it tastes like. Why is that? Because everything they put out, by the way, not the greatest sandwich in the world. But every time it tastes just like a freaking Big Mac is supposed to taste. You do not go to Boston and it tastes like a Whopper. You don't go somewhere else and it tastes, no, it tastes like a freaking Big Mac every single time. And standard deviation is what we use to get there. Because everything will always have some amount of variation. That is, in anything there is always going to be some, if you want to think of it this way, some wobble. There's going to be some change that occurs naturally. Now, for instance, in people, heights, weights, obviously there's going to be some kind of a wobble deal. You're like, Mr. Grimm, what are you talking about? Well, for instance, this person here is a little shorter than the average. That happens. This person's a little taller than the average. Well, how about that? It happens. This person's a little skinnier, a little fatter, whatever. It happens. It's called genetics. Okay? But when you're running a business, there's there's going to be some variation, some change from time to time. Later in the day, Jack, did I do that right?
Yeah.
Hot dang. Later in the day, Jack's going, I don't care anymore. How is his work quality going to be at the end of the day versus in the morning? That's Trenton. No, that's Trenton. God dang it, I should have gone with my first guess. Trenton is not a morning person. No siree, Bob. When Trenton walks in, I got 2 hours of out of him before he finally wakes up. Now he's good for about 4 hours in the middle of the day, and then off the other end of things. Okay? Now you've got some people like Naomi over here that are just perfect all day long. Okay? Why is that? Is it a self-driven pride thing? Yes, whatever. You should all learn from that. But whatever. But some people are like that. By the way, if you use a printer device or something like this, sometimes, after it's been used multiple times, toward the end of the day it gets hot, right? Things don't work quite as good as they did before. Yeah, there's always going to be this natural variation. That happens, right? There's going to be this change, wobbling. Sometimes I can find out why. Sometimes it's because we are morning people and we're not morning people. Sometimes it's coffee content that matters. Okay, we're not robots, most of us. So we're always going to have these sort of things. All right, even robots, even machines have times of day or whatever. Maybe they do less, better work, whatever. But here's the thing. We study variation and we study standard deviation. We study this business because as a business person, we really want to get tight quality controls on things. And we will do that a lot later this year. We'll talk about it a lot later this year. But we also use it to describe the shape of a graph. Now, the other day we said this graph is symmetric, yes? Yes. Is this one symmetric? Yeah. Do they have almost identically the same mean? Yeah. Are they the same distribution though? No. Why not? Because this one is more spread out. Wouldn't it be cool if we had a number that described that, how spread out it is? Well, we do. And what it's called is the standard deviation. And it is a measure of how spread out our data is. That's it. And that standard deviation, just like everything else, can change from day to day to day. Yes? Think about this. Think about the most positively over the top nicest person that you know that never has a bad thing to say about anybody. No, I don't think it's you. I don't know you that well. I don't think it's you. Okay, but whatever. But listen, to the point where they're almost obnoxious because they're so nice. Okay? Now, Mrs. Daly used to be that person I knew really well, like it was like that. Oh, good morning, everything wonderful. You knock it off. That is not true. But listen, if you see a person like that, you come in and they're just like kicking the tables around or something, well, you know there's probably a problem there. Okay? If you know someone that's a little more dour like myself as a general rule, and they're coming in one day and Mr. Groom, as you see him busting a move somewhere, like what is going on with him? That's pretty odd. If you come in one day and Mr. Groom's a little sourer than usual, perhaps, you're kind of like, whatever. Okay. But if all of a sudden I'm Mr. Excitable, I wonder if there's something weird there. It's odd. We catch ourselves by that. And listen, what I want to see is this. As you go through this business, we want to see how spread out it is. If everything's pretty tightly clumped, okay, then it doesn't take very far out of the ordinary to go, hey, that's weird. But if there's a lot of variation, everything's just all over the map. Portland, for instance. You walk down the street in Portland, is there anything that shocks you anymore in Portland?
No.
Not really. Not really. Now you move back to my little hometown, you walk down the street there, just pick any random person out of Portland, drop them on the main street of my old hometown, boom, that's weird. Yeah, it is weird. It is strange. It's out of the ordinary because pretty much everybody in the hometown pretty much looks like, between here and here, pretty tight, right? In terms of what they look like, behavior, whatnot, right? So you bring in some random rapist guy and drop him in the middle of town. It stands out like a sore thumb, okay? You bring in one of your little eco people, Portland, like pedal your bicycle around, sell your vegetables kind of guy with the long hair and the beard and the whole bit. That stands out the other side or something. But it's really weird. But like you drop a guy in town that's like more like from Wyoming, maybe he wears a cowboy hat. It's just different. It's pretty much normal-ish. It's a little different. Not a lot of our people wear cowboy hats, but I don't think anybody would really blink an eye about it. Like, I'm wearing cowboy hats. We'd think, Jesus, not rodeo season, but okay, whatever. I'm okay with that. I mean, everyone back home, everyone's got a cowboy hat they wear to the fair. All right, we're going to play cowboy this week, all right? But other than that, it doesn't really get worn that often, okay? Now, here is the deal. As we've talked about, in the population, we have parameters, yes? And again, as always, who knows these? Only the good Lord himself does. That's the only person that knows them. You cannot go out and find all wild jackals everywhere and measure their weights. It's not possible. And even if you did today, you started today, you'd finish 3 weeks from now, guess what? One of them is dead, or it's ate a bunch of stuff and got fatter. I don't know. It's not going to be an instantaneous measurement, right? Because I can't know everything at the same time. All right? So, there will be a standard deviation of the population. Now, watch carefully. I'm going to show you this. I'm going to show you. I'm going to talk about it right now. This is lowercase sigma. I'm going to show you how to draw it. I always wanted to teach like 3rd grade penmanship or something. So watch, this is how you do it. You start like this, and you come across like so for a ways, and then down and around, and back up, leaving a little tail. That's it. That's it. Let's practice again. Oh, wait, here, let's do this. Okay, boys and girls. Huh? So you start the center line, see? Come across, down to the bottom line, boop, back up and leave a little tail. Except you can't really see the tail because it's on the dotted line, but you get the picture. Okay? That is lowercase sigma. Again, Emily. Emily, again.
Oh, that was on the tail.
Mm-hmm.
I think the first one was the worst.
It was. And then I tried to get cute, and then it screwed it up. So, whatever. That is lowercase sigma. I don't really care. As long as it doesn't look like a frickin' zero, I'm pretty happy. It should have a tail on it. Okay? It's not that hard. You'll figure it out. Now, is that cool? Is that cool? All right. Now listen. Sigma squared is the variance. Mr. Grimm, is that just the standard deviation squared? Good job. It is. That's right. That's right. And so the variance, again, has to do with that idea of how much change there is, how much wobble, how much whatever you want to think about it is. It's out of the ordinary. There's always going to be this. We're not all the same. If everyone was the same, it would get really old, yes? Sometimes you think, golly, I'd like to work with myself, but if everyone was like me, it wouldn't be very fun, I don't think. Just stop it, okay? But listen, like when you go to Portland, people say, oh, you got to keep Portland weird. To me, Portland is this. It's a 5-gallon bucket with nothing but spice in it. All right, there's a cup of cumin. All right, let's put a cup of cinnamon in, like a cup of allspice, a cup of chili powder, a bottle of sriracha sauce. Stir it up. Hey, that's Portland. To me, there needs to be a little meat. All right, you need some bland in there. Maybe a carrot or two, whatever. Something to kind of make it, palatable. If that's nothing but a bucket of spices, it gets a little weird after a while, right? Now, as you know, we don't know anything about the population, so we take a sample, yes? Mm-hmm. And we compute the statistics. Yes? And the statistics are the same, right? Characteristics, right? But from the sample. So, when we write this, S, most books write S. Mr. Groom usually writes S with a little X next to it. I do that for 2 reasons. This is how your calculator, your TI 83s, 84s, 89s will show it. But also because my S's end up looking like 5s frequently. So if I put a little X by it, you're like, I bet that's not a 5, Mr. Groom. I bet that's an S. Okay. This is the standard deviation for the sample. And of course, S squared is the variance for the sample. Yes? But again, samples have the S's, populations have the sigmas. Nice. It's muy bueno. That's it. That's it. Do I need to go up higher, yeah? Emily? Yeah. Is that better? That more better? Yeah. Yes, yay. So again, as always, which one will we be computing? We will be computing these ones, yes? And then we will be saying something about these fellers. As always. Now, is that good? Now, again, you want to practice it again? It's like this. Weep. Yes. So listen, these two guys right here are both parameters because they're characteristics of the population.
Okay, that's what I mean.
That's just, yeah. But again, we don't know them, so we compute a statistic from the sample. Nice. All right, so Lindsay goes, that's great, Mr. Grimm. How do you find this thing called sigma? Well, we're not going to compute sigma, dear. We're going to compute S sub x. Now, I'm just going to always use sub x. Don't freak out. It's just the standard deviation of the sample. How are we going to do that? Let's come up with some numbers. 1, 2, 5, 14, 27. Oh, crap. It's 3, it's 8, it's 22, 49. I'm going to make that a 3. Now it adds up to 50, okay? Now, I did it on purpose. I did that on purpose. What is the average of this set of numbers, friends? What is the average of that set of numbers? It's 10. It's 10. That's why I did it. Otherwise, it would have been 9 point something, and it would have pissed me off. It's 10. Okay? I didn't want that. I wanted a nice, clean number. All right. Now, let me ask you a question. Bree, the average number in this sample is how far from the mean? Now let's slow down and ask that question again. On average, I don't know. Let's find out. On average, how far is each number away from the mean? Okay? That's kind of what I'd like to know. How spread out is it, right? If the mean's here, how spread out is it from there? Yes? How would you figure that out, distance from the mean? Yeah, still asking you. Yes, you do know. I feel like I should probably subtract them, shouldn't I? Right? I feel like it. So watch. Hey, what is 1 minus 10, Mr. Grimm? I feel like it's negative 9. Uh-oh. Uh-oh. That ain't key. Nope, we're back. Sorry. 1 minus 9, what? No. 1 minus 10 is negative 9. Add a baby. 3 minus 10 is negative 7. 5 minus 10 is negative 5. 14 minus 10 is 4. And 27 minus 10 is 17. Now let's average those, shall we? So let's plus them up and we'll see what we get there. What? I don't know. What did you guys get? I don't know. Oh crap, it's 0. That means the average distance is 0. Well, that's not helpful. I'm not blind, friend. I can see that they're away from there, yes? So now at this point someone goes, hey, just make them all positive. It's a good idea, except, this is how the big kids do it. Not only do we subtract them, we square them. Now, when you square something, of course, it makes it positive, yes? So that's helpful. But not only does it do that, it actually weights things. So for instance, if I tell you that someone fails a class, you're like, okay, cool, I guess, whatever. I didn't tell you how bad they failed, did I? So if somebody really failed, I mean like a 2% in the entire class, which is pretty hard to do. Yeah, how does that affect the total average? What does that do to the spread of the data? Boy, it really stretches out a lot. And here's the thing. When you square a number, they become large in a hurry, correct? And so by squaring them, this is what the big kids have determined over the years, it actually penalizes you from being further out. And so this actually is a little better job of then saying just taking the absolute values. Okay? Now let's add those together as if we were averaging them, shall we? Did you know 17 squared was 289? Why not? I don't know. I just remember that Mrs. Dutton said in 3rd grade, oh, you're done with the 12s? Keep going. Memorize up to 20 multiplication tables. That was cool.
You were like smart.
No, I really wasn't. I was kind of annoying about that, but it was good. I was good at like little stuff. But it's come in handy as a math teacher, but otherwise I'm not really sure it would be helpful at all. What does this come out to be when you add them together? A little calculator? How much?
460.
460. Look at that. One Ford engine and another Ford engine. How exciting. Now, I still would like an idea of an average, wouldn't you? And so when we do an average, we normally think, well, we should divide by what? The number that there are, yes? Well, I'm here to tell you, friends, I'm here to tell you that's a little different for standard deviation. You divide by one less than there are. I'm going to tell you momentarily. Okay. Now, this thing right here is, what does that come out to be? 115. This thing right here is our sample variance. And if I want the standard deviation, I simply, square root it, obviously. And so the answer is 10 point something, yes? What is it, 10 point? It's not 10.2, is it? 10 point, it's almost like 10.7 or something, I think, 10.8. 10.8? Square root of 115 is 10.7. Nice. This thing right here is how it's done. Now, friends, here is the formula. It is very straightforward. Let's do it one piece at a time. We said we wanted a minus first, yes? So if you're going to minus first, you better put it in parentheses, because the last I checked, that's the last thing we're supposed to do. So watch carefully. I will write it like this, and then I will explain myself momentarily. X sub I, Mr. Groom, because I have multiple values of x. Did I not? In this case, I had 5 of them. So I'm going to take each one of them and subtract the average off, yes? And then I'm going to square that. That's what we did. And then what did we do? We added them. I'm going to show that right here like so. I hate sigma. It's so scary. It's not scary, for God's sakes. Shh. So friend, in the case of the one we just did, we added 5 times, yes? We went from the first one, second one, third one, fourth one, fifth, and we added 5 of them together. That's all I mean. This is uppercase sigma. And whenever you see uppercase sigma, it always means add them up. Every single time. And then when we were done, what did we do? Why, Mr. Groom, we divided by n minus 1. Because we had 5, but we got rid of 1, we divided by 4. Now, Josie Hanna over here is going, but Mr. Groom, why? Well, listen, if you take a 400 level statistics course, which you probably will never do. By the way, it was not a fun course. It was not the worst one I ever took. Oops. The worst stats class I ever took, which is also the worst class probably I ever took, was, I kid you not, Stat 666. I kid you not, I got a charity C in the class. I have no idea what it was about. It was sitting there going, what is happening here? I have no idea what you're talking about. And there's one teacher who was blubbering at the board, and 2 people were sitting in the classroom going, that's like so-and-so's theorem, isn't it? Oh, yes, yes. And the other 2 guys were going, what are they talking about? I don't know. What is it? I don't know. We never one time did anything with data. It was all just theory. Wow. Snooze a Rooney. All right? Yeah, nasty class. Now, but anyway, in those classes, in 461 is where you show this, you will show why you divide by n minus 1. We call this an unbiased estimator. You don't need to know it. This is just how we're going to do it. Okay? This is how it's done. If you really want to know why it works the way it works, take another class. You can figure that out. Listen, this is how we say it. It's beyond the scope of this class. This is kind of like back in 3rd grade when the teacher told you, or no, in first grade, When the teacher told you you can't do 1 minus 4, although you can't do that. She lied to you, all right? But it's okay. You have to, because otherwise you freak the poor little kids out. Oh, it's too much. I can't do it. Yeah, what? Miles. So, friend, this is all you need to memorize. Do I need to memorize this one or this one? Listen, I don't really care which one you memorize, because they're basically the same, aren't they? For God's sakes, just don't memorize both of them. They look stupid. Okay? You just look stupid. So don't do that. Okay? One or the other. It's one of the few things. But listen, if you think of it this way, Ashley needs a way to remember it, so this is what I like to do it. I call it the average. But watch how I do it. Average, because it's not quite an average, right? Squared distance from the mean. This is the variance. If you remember that definition, then the formula should come up to you pretty easy, yes? It's an average. That's the only part that's weird, because it's not really dividing by 5, so it's not really an average, but it's kind of an average. Well, how do you do averages? Well, you add stuff up and divide, so I got that. And then, oh, it's a squared distance from the mean, so I better subtract them from the mean first, find how far away they are first. Okay? Yay. It's not that hard. Now, how do I use it? That's where the fun begins. Okay? Yeah, I promised you it's going to be fun. Okay? Now, this chapter's amount that we do with it is kind of a snoozer in some regards. But as we move throughout the rest of the year, the stuff that we do with standard deviation is actually going to be a lot of fun. Okay, but this, I'm not going to lie to you. The first kind of day or two is kind of like, oh, wasn't that fun? Not really, no. But it's necessary. Necessary. So, suppose I told you that I had a symmetric I'm going to go with the symmetric. I'm going to draw it symmetric. Suppose I had some sort of symmetric distribution. I don't even know what that says. Distribution. There it is. With a mean of 110 and standard deviation of 16. Okay. What?
Okay, on the last page I was going to ask you something, but I don't know what
Well, what's your question?
So the part that I was confused about was, so I didn't think, so 10.7 was your end answer for the standard deviation, right? So you squared everything and then divided it by the same number as you
4.
Yeah, 4 if you didn't square anything, right? So if that worked out before squaring something, you still would have just divided it by 4.
So you're going to square stuff, add them together, divide by 4, and when you're all done, square root the whole mess. Whatever your answer you got, 115, that was already divided by 4, right? Then square root whatever that answer is.
Okay, and that wasn't the variation? That wasn't...
Okay, listen, before you square root it, it's the variation. After you square root it, it's the standard deviation.
But what I'm confused about is can you just go back to it real quick?
I just aim to please, brother.
So when we first tried to add up all the numbers, but they came to 0.
Ah, listen carefully. They added to 0. Emily, this is why they added to 0. When I was a kid, Emily, I was a fat kid. I've told you this. It's no big surprise. Even my eyeballs were fat, apparently. Never had a butt, though. Never have had a butt. No matter how fat I've been, I've never had a butt. Anyway, whenever I teeter-tottered with my buddy Jimmy, I'd have to sit in here and hug the fulcrum. And Jimmy, who was scrawny, would sit out here and put his legs out backwards to get enough muscle on this end of things to balance me, because he was a scrawny little devil. Okay? Sometimes Keith would join us, who was also scrawny, and they could move in just a little ways and then balance me out. Only if I was teeter-tottering with Andy Hawks, who was way fatter than me, only then could we actually sit and teeter-totter like normal kids-ish. Because we were more or less the same. He was way outweighed me, though. Like in high school, I was probably 220, 230. and he was like 315. I don't know. Okay, so, but whatever. So even when we were little, he was still fatter than me, whatever. But anyway, listen, it balances out. The average is always at the fulcrum. Therefore, it is the balance point. So if you say that, then these people, if you go out here certain ways, out here certain ways, out here certain ways, and if you picture them as little people that weigh the same amount, right? If they weigh the exact same amount, then if you put a guy here, way out here, he has more torque, yes, than a fellow that was in here. So you would have to get a few more of them in here, the same weights, these are all the same weights, in order to balance it off, because this distance here, this is equal to this distance plus this distance. That would balance it out. That's how the average works.
Yeah.
It will always equal 0 if you don't square it. Always, always.
Oh.
Always, always.
Oh,
Any data set.
Okay, so you were just acting surprised?
I was acting surprised.
Okay,
I did a good job, didn't I?
Yeah, see,
I was in drama in an earlier
I
life.
thought that it was supposed to work out.
No, it never works out. It's always 0. That's the cool thing about it. It will always be 0. Now, although sometimes I'll be real honest sometimes. Sometimes some kid will go, it's 2. And I'm like, oh crap, it didn't work out right. I bet it's just some clown can't add. Hey, go ahead. So I squared in order to make them all positive.
Right.
Okay, now, let's draw this picture, shall we? Symmetric?
Yeah.
Where's the average go? By God, right in the middle. Now, let's count out standard deviations. Well, Mr. Grimm, what do you mean? Well, if I go over 1 standard deviation, it puts me right about here. How did I know it was 126? Because I added 16. That's 1 standard deviation. Let's add 16 more. Yo. $100 and 94. And by the way, I did an amazingly good job of drawing it this time. Sometimes I do a lousy job. I did a really good job of drawing it this time because look where the third deviation sits. It's way over there in the corner. You see that? Way over in the corner. Now, there's some pretty cool things that we're going to talk about standard deviations here in a second, but let's just eyeball this. This is plus or minus 1 standard deviation, yes? Now notice I wrote sigma this time. If you see me, if I write on the next one, if I do this, do not freak out, because I will use them interchangeably when I speak about standard deviations, okay? I will use them. One time I'll write this one time I'll write that one. Mostly because when you go look at the book, sometimes they use this one, that one. I want you to feel comfortable either way in this case. We will only ever compute Sx, but when we're talking about concepts here, we may use sigma or we might use the other one. Does that make sense? Plus or minus? Now listen, friends. If you were to look at this and go straight up here, like straight up here, more or less, does that look like maybe more than 50% of the population?
Yes.
It does. It does look like a little more than 50% of the population. It turns out, Ziegler, there's actually a pretty cool rule for it, and it goes like this. Anytime you have a symmetric distribution, and your mean is always in the middle, because it always is. If you come over 1 standard deviation or negative 1 standard deviation, so between here and here, dude, that's 68% of the population. Now I will say 68, but technically it's approximately 68%. 68% of the population was between here and here. Between here and here. Now I know what you're thinking. Could I do decimal versions of my percentage of these? Yes, we'll do that later on, but not today. Okay. Mr. Green, what about within 2 deviations of the mean? Well, between here and here, is that most of it? Turns out it's 95% of the population. By the way, if you are outside of the middle 95% of the population, are you weird? You are. I'm not bad. I'm not judging. I'm just saying. Okay? Height, weight, whatever is your deal you're talking about. If you're outside of the middle 95%, you're a little off. That's a little weird. There is a sign right here that says, "Welcome to Freakville." There's also one on this end. This one, we'll call this one Welcome to Freak Town, I guess, because it'd be weird if you're going to opposite directions and came into the same town, right? Yeah.
It'd be freaky.
That would be really weird. Yeah, I'll just go with Freakville. I like the town of Freakville. It's pretty cool. Oh, Mr. Groom, what if I came out 3 standard deviations? Oh, Judas Priest, man, I don't know. Well, that's more than 95, yes? Anybody want to wager a guess as to how much it is? 99.7. Now, it's a calculus thing. Again, you would learn if you took a calculus-based statistics that you'd learn exactly where those numbers come from. Okay? It's actually this gross integral. And so, yeah. But you won't have to do it. You will use your calculators to find those values later on. But these are the rule of thumb. This is what is called the empirical rule. The empirical rule. It holds for any symmetric distribution. Later on, when we get into the normal distribution, which happens to be symmetric, we will no longer go with approximately. We'll find the exact by God figure. But this only works, empirical rule works for any symmetric distribution. Any of them. Okay? Any of them. Nice. Yeah. Abs, you got that? Now abs, up here, dear. Between if I said it like this, what percent of this population is between 94 and 126? You would say 68%, because this equates to 1 deviation on either side of the mean, yes? And away you go. Huh? Now, Mr. Graham, give me an example that is more closer to my home life that I feel like. Okay, good. Glad you asked. Hannah. Boy, I have to stop myself. I don't even know why. I haven't seen your sister in how many years? I don't even know. How many years has it been? 3? 4? I don't know. And I don't know. It's weird. All right, so listen. I happen to know that women's heights in America, I happen to know that the average is 66 inches. I know the standard deviation is roughly 2 inches. It's not exactly, that's close enough for government work. I'm just going to go with it. Okay, I don't need a calculator if I just keep it whole numbers. So that means like this. I know it's symmetric. I happen to know it's normal, but it's symmetric. I know that. Meaning that I am just as likely to see a short person as I am a tall person, yes? And so 66 is here. Let's count off by standard deviations, shall we? Okay. 68, 70, 72, 64. Well, that's kind of crappy. Oh, shoot. Idiot. 62, 60. It's supposed to be symmetric, in case you're wondering, okay? So listen, this is ladies. So what percent of ladies are between 62 and 70 inches tall? Well, Mr. Groom, that's right here. And right here. That's lousy. That's supposed to be symmetric, in case you're wondering. But look, that's 2 deviations this way, yes? That's 2 deviations this way. So your answer is 95% of them. Now let's think about that. 62 inches is 5'2", yes? Do you know many ladies that are shorter than 5'2"? You don't know a lot of them. Okay, listen, we're not going to mention names. Do you know a lot of ladies that are taller than 5'10"? No. In your mind, you're going, I got like 1 or 2, Mr. Groom, but as a general rule, how many ladies have you met in your lifetime? A lot. The fact that you can name 1 or 2 of them is showing that you don't know many that are taller than that. As a general rule, I know a few shorties, I know a few talls, and I know a lot of just in-betweens. You know how tall they are? No, that's the whole bit. It doesn't stand out in my mind, yes? Right? I walk by the average person, their height doesn't mean anything to me because I just think, oh, they don't stand out. Now, I think you use height usually because how can you get offended? It's genetics, get over it. No one's making fun of you. That's just how it is. Now listen, 95% of them. So Miles goes on Match.com. I don't know why you're going on there, weirdo, but he is. And he goes, look, I'm going to really restrict I only have certain qualities for dating. He goes, Mr. Groom, my rules for dating is they have to be taller than 5 foot and shorter than 6 foot. So, that's from here to here, Miles, which is plus or minus 3 deviations. How much has he cut his dating population down by?
Not much.
Well, if 99.7% of them fall in here, he has restricted a whopping 0.3% of the population are outside of his dating criteria. Sorry, you're too tall. I will not date a 6'1" gal. I'm sorry, you're 4'10". Sorry. Ooh, I draw the line at 5 foot. Okay. He is not cutting it down by much. Yes? Ashley, however, says, Mr. Groom, I also went on Match.com, and she goes, the guy must be... No, it's not Ashley. What am I thinking about? Blake. We're talking about women's heights, and I have to change my whole thing. I have to do men's heights or something. Anyway, that would get weird. So Blake is going online. He goes, Mr. Groom, they must be taller than 5'10", or 70 inches if you prefer. They must be. By the way, I feel that. That's cool. Now, from here over is how much, people? Well, look, I don't know. But I know that between this guy and... I know that all this in here is 95%, yes? That means there's a total of 5% between here and here, yes? Total? So 2.5% out here. Attaboy. You restricted it by quite a bit. Okay? Other people would just be like, some people like Matt, they wouldn't put a restriction on there at all. The number of hits that Matt gets versus Miles, if everything else is the same, there's no difference really, yes? Miles cut out a whopping 0.3% of the population, and Matt just goes, any size lady will do for me, height-wise. All right? Let's rock and roll. Yeah, she's a 7-footer. I don't know. Okay? It's fine. Now, it's very straightforward, very easy to do. Now, here's another. Ooh, no, wait, this is a test. Mr. Groom gave this test the other day. Ooh. Watch me as I draw these out. I can't add.
It's okay, it's only math class.
I know, right? Fortunately, I always like to tell people, yeah, it's all right, I'm not a math teacher or anything. But, yeah, there you go. Cool. The average of my math test was 80%. Okay, that's pretty good, I guess. Whatever. I guess. By the way, there's a guy I used to teach with. His tests always look like this compared to mine. Same average, but what about the standard deviation? It's a lot smaller. Why was that? Does he have a lot smarter children than me? No. What happened every year is he made the most ridiculously easy test to the point of absurdity. And he's like, boy, my kids did really good. I'm like, well, I'm not surprised. You're giving points away. You're like, seriously, circle the number 6. This is a pre-cal, bro. I mean, you probably ought to make the test a little harder than that. Anyway, everyone, of course, I want to take Mr. Craig. He's easy. Okay, well, good for you. That's fine. But my class is a little trickier. Listen, if you got 100% on my test, if you got 100% on here, are you weird?
Yeah.
That's pretty weird, right? Comparatively speaking to the class-wise, that's kind of an odd score, yes? It is not very likely that you're out here, yes? As a matter of fact, I would argue that if you are, the probability that you are greater than 98 is only 0.15%. Because remember, from here to here is 99.7, yes? That leaves 0.3% for the outsides, half of which is on the upper end, yes? So it is pretty dadgum weird if you got up around 100%. It's pretty weird. It's not likely to happen. Of course, as we know it, someone has to win the lottery. It's also not very likely, but sometimes, it happens. Now, Mr. Groom, I got an 84 on your test. Okay, good for you. That's a decent score. Is it a great score? It's not a great score. As a matter of fact, here's my question. If you came over here to 86, what percent of the people did worse than you? Well, let's find out. So we know that from here, the middle, over to here is over to 86 is how much? It's not 68. It's 34 because it's half of 68, yes? Now again, here's the picture. We know that within one standard deviation, it's 64 total, yes?
68.
I'm sorry, 68. The 4 came from what happens. If I take half of it, I get 34. So it's 34 on this side right here, yes? So here's my question to you, Hannah. From here down is how much? From the middle down is? I didn't write you a number, so think about it. It's symmetric, and it's cut right down the middle. It's symmetric, and it's cut right down the middle, and I'm going all the way that way, 50%. That's right. So what percent of the people are less than 86?
84.
84%. Okay? Now, when we're doing this business, you're like, okay, that's not very hard to do. So, Mr. Groom, you only scored an 84. Well, 84 is not a full deviation, is it? It's not a full deviation over. It's part of a deviation, yes, but it's not the full amount. Can I find that amount? Can I find out what percent is less than this? You can, but not today. Okay? So, when we're talking about the empirical rule, you have to be on these, whole valued numbers of deviations, okay? But later on, we're going to get into the nitty-gritty of it. But here's my question to you. Suppose a person did score an 84%. Well, this is one standard deviation. What is this guy going to turn out to be? Point something. It's point something. But listen, if I did 86 minus 80, right? And then divided by 6, that's equal to one standard deviation, right? So, but if I did 84 minus 80, divided by 6, it's, 2/3, right? Or 0.666666. Yes? Right? This idea of how many z-scores, how many standard deviations you are from the mean is a big deal from the mean. And we call it a z-score. This is, in conjunction with standard deviation, probably the most important topic that we learn all year that we'll keep using again and again and again. So next chapter, and the next chapter, and the next chapter, and every chapter from here on out, we'll talk about z-scores. Oh my gosh, they're so easy. This is how you do it. You go z equals x minus the mean divided by the standard deviation. But Mr. Groom, on this next problem, you might write it this way because you're a jerk. You're right. I might write it that way. I might write it with using the statistics as opposed to the parameters. All right? But I will never mix parameters and statistics because that's disgusting. Which one now? Where at, dear? This one? That's mu. And that's the mean of the population, right? All right, so we can practice that too. Technically speaking, if you're a good Greek person, it looks like this. That's how you're supposed to write it. I just kind of write it like that. But it's fine. Okay. Like if you were in Greek penmanship class, you'd do this. And probably there'd be a line here, and I'm guessing like that. I don't know if they had ruled paper back in the day. But I think if you did, it would look like the J's tail would hang down, and so forth. But again, it's not really that big a deal. As long as it doesn't look like it. This is not mu. That's disturbing. Okay? So as long as it's this pointy looking M, I'll probably figure it out what you're talking about. Okay? I'm pretty good that way. Okay? Now, so z-score is a big deal. And a z-score is literally this. It is how many standard deviations above or below the mean you are. Now it's important that I say above or below, Mackenzie, because on the problem I just drew up there, the picture looked like this. The mean was 80. If you scored a 72, well, first of all, I think you suck, but there it is. It's what you did. And the standard deviation was 6. Oh, Mr. Groom, can I figure this out? Yes. So z would equal, but notice it's 72 minus 80 over 6. That's negative 8/6, which is negative 1.333. But notice the negative means, did you score above or below? Well, you scored below. So the negative will tell me which direction to go. Yes? Positive, you did good. Negative, not so much. Not so much. Now, I need, who is a track person? Yes, shake of hands. What track event do you do, sir?
No, I'm playing at Josie.
Oh, thank you. Josie, yes. So, fart. I close my notes. One moment, please. So Josie, as you know, is one of these weird people that likes to run long distances. No offense, just saying. Here we are. We're having a great conversation as we're running 12 miles. I know, right? Totally. I know. Isn't this fun? No. Weirdos. Anyways, but listen. Listen, I have respect for you. I just don't get it. I don't get it. But listen. Listen, so the average for a particular race for the 3,000 is how long? Oh my God, I don't run the 3,000. I only run the 1,500. Just tell me a number.
You mean at time?
Yes.
11:30.
11:30. I'm going to go with 11. I'm just going to write that as 11.5. That's okay with you, okay? That's fine. And I'm just going to make up a standard deviation. Unless do you know a standard deviation? I doubt you do. So, did most people finish within a minute of that?
No.
3 minutes of that?
Well, yeah.
If I went with 3 minutes on either side of that, would that be a good amount? So you're saying this is average? That's average for you. Is that average for you, or is that average for a person who's just kind of an average person running?
It's a little faster than that.
Well, then let's go with 12 minutes. Is that good? 12 minutes?
I'd say 12.5.
12.5. Okay. Listen, friends, when you're a teacher, you can make up your own numbers. Okay. Now, would most people finish within 3 minutes on either side of that time?
Yeah.
2 minutes? Would most people finish within 2 minutes on either side of that time?
Yes.
Within 1 minute.
Probably.
Within 1 minute. So listen, I don't know, I'm just making this crap up as I go. So you too, again, could do this. But if you're saying in your mind that most people would finish within 1 minute, right? What you're drawing is a picture that looks like this. Am I not? Right? And, where would Josie be if Josie's a fast person? Which side would she be on? The lower side, right? Which is, for me, it's that way, but for you, it's that way, right? The lower end of things. So the speedy folks would be down here, and the not so speedy on this end, yes? There's 2 E's in there. Nice. But listen, if most people finish within a minute on either side of that, yes? A minute on either side of that. We know this is about 3 standard deviations, yes? And if you do 1 minute divided by 3, you get like 0.33 of a minute. Do you buy this? Right? So if a person were to lay this off, and I'm just saying let's just do this, 12.5, let's count out, so that'd be like 12.83. Oh, I can't do that in my head. 13.16, 13.49, which makes sense because it's 13 and a half. Duh, Mr. Groom, you idiot. Going this way, it's a 12.17 or something. And then you minus that again and you get something like 12.86, I think. What? 11? Oh, I'm sorry, thank you, 11. Thank you, my bad, thank you. That's not right, Mr. Groom, you gotta subtract 33. 8.4, there we go, yeah, that'll work. And then like 11.51, right? Okay. So, like, if this was true, if this is true, it's symmetric, right? What is the probability that a kid, first of all, actually, let's write it this way. Let's do it this way. If a person scores on this thing down here, if someone has, like, say Z sub Alyssa, so this is Alyssa's Z score, and Alyssa gets negative 1.2 for a Z score, and Mackenzie came out and ran with us today, and Mackenzie, she's not, are you a runner?
Yes.
Oh, are you? No. Good. I'm just asking because I just want to see. But yeah, negative 0.2. Who did better in this race Alyssa or Mackenzie? Alyssa, because when it comes to running, you'd like to do it faster, which is further that direction, yes? If this was a math test, who did better? Mackenzie. But neither one of them should be bragging, yes? In this case, yes? They're both below average on the test. Mackenzie did a little less worse, if you will, if it was a test. But if this is a race, Alyssa did okay. Now, Alyssa, how fast did you run it? How fast did Alyssa run? How fast? I don't know. How do I know? Well, I don't know, but I know Z is equal to this thing, yes? And I feel like I know this. I don't know that. I feel like I know this and this. True? This is why we make you do algebra before this class. Womp womp, 0.33, 0.33. I don't know what that is. Somebody figure that out for me. X minus 12.5 plus 12.5 plus 12.5. 1.6. Yes? No, that's not right. You idiot. The other way around. What? 1.06? There we go. Good call. Negative? Negative. Yes? But wait a minute. Mr. Groom, look at this. 12 and a half. I'm going to write it like this. 12 and a half minus 1.06 is equal to Alyssa's time. 12 and a half? Well, that's the mean, Mr. Groom. That's right. And look, she took 1 minute and 6 off of, if you will, the mean. She's that much faster. So what does that come out to be? 11, no. 11? Yes, 11.44, yes? Good for you. Okay, whatever. Good for you. Now, Mackenzie, it's good. You're fine. No, but listen, you're not a runner. Neither am I. Maybe have more respect for you if you're not a runner. I don't know. So negative 0.66. So in other words, she's going to run it 66 hundredths of a second faster than the average. I don't know what that is. 11.94. You should check my math. That feels funny. 11.84. Is that right? I feel like that's closer.
11.84.
Bam! Nice. But Mr. Grimm, it's only 4/10 of a second. Well, first of all, that's a lot, so I wouldn't be bragging about it's only. But second of all, when you think about this, a tiny z-score doesn't necessarily equal out to a lot. In this case, tiny z-scores are just like 1 and 1.06 and 0.66. If you were doing it for a house population in town, what do you think of the average house prices in St. Helens? I don't know. I'm just going to make up a number. 200,000. I don't think it is, but I'm just going to make it up because I can do it. Hey, what's the standard deviation of house prices? Is it $1? No. 45,000? Sure. Okay. You own a construction company. You want to build the most expensive, wait for it, the most expensive 16% of homes on the market. None of these little crap boxes for you, lady. But not just glorious mansions either. Want some rich people, but not some ridiculously rich people. So watch carefully. Later on, we're going to do this more in depth, but she wants the top 16%. How on earth will we find that? Well, listen. Within one standard deviation on either side of the mean, we know this to be 68. Yes? That means that there is a whopping how much total out here? 32. And half of that is 16. So what she wants to do then is she wants to go one standard deviation, you see, above the mean. So in a case like this, I probably wouldn't write it like this because it's just exactly one standard deviation. But later on, I'm going to say it's be like 1.2 or something. I'd want to write it like this. And I would go, she doesn't know this answer, minus the mean over the standard deviation, which was, we say 45,000? Right? Yes. So times by 45,000? I just stopped. I said, sorry. The other day I was coughing ridiculously in one of my classes. I couldn't stop. I'm like, I'm doing my Hillary impersonation. But then I just had a glitch just then, apparently, like she did too. So I don't know. There we go. Plus 200,000. Plus 200,000. So you should build houses that are at least that expensive. Yes. Do not go any less than that. You won't be in your niche. Someone else goes, I want to build for the middle whatever percent of the market. Well, good for you, okay? They're going to change it up and look a little differently at this problem, okay? We spend a lot of time with z-scores. They are a big deal, okay? Later on, we'll actually call them, there'll still be z-scores, but we'll actually use them in a different fashion. But the same things will occur every single stinking time. Now, I've talked enough today. You can start doing the homework for chapter 3. Did I print it out yet? I did. Good for me. You will, at some point, Abby Austin, get to a point where you see this thing. Listen carefully. You will see this. A feller by the name of Chebyshev. We have not talked about Chebyshev yet. We're going to talk about him on Monday. That's not going to mean you can't read about him. But if you see him, don't come cry to me, because we're going to pick you up right there on Monday. Okay? You may, dear. It's there right here. Just a minute, Lens. Yes.
What are we doing Friday?
I'm not seeing you Friday.
Yes, we are.
Nuh-uh.
We had this class Friday.
Oh, I'm off a day. Yes. Friday we're talking about Chebyshev. My bad. Friday we're talking